learning outcomes. After studying this module, you shall be able to know about different structures of various metal carbonyls and about various techniques that are being used in the determination of structures of metal carbonyl complexes. You will also be able to identify structures of metal carbonyls and to evaluate the electron count of the complex. Introduction. Carbonyl ligand displays a variety of bonding modes in their metal complexes such as terminal and bridging. Due to large number of bonding modes, the structural determination of metal carbonyl complexes is extremely important. The structures of metal carbonyls are determined with the help of various spectroscopic and diffraction studies such as X-ray diffraction, infrared spectroscopy and electron diffraction methods. Mononuclear metal carbonyls have only linear metal to carbonyl linkages. The polynuclear metal carbonyls have some other type of linkages also, such as metal-metal bonds and bent metal carbonyl metal linkages. The terminal and bridging carbonyl groups can be distinguished with the help of infrared spectroscopy. The terminal carbonyl groups exhibits absorption in the range of 1850 to 2125 cm inverse, while the bridging carbonyl group does so in the range of 1700 to 1850 cm inverse. The shape of the metal carbonyl depends upon the nature of hybridization on central metal ion. Tetrahedral, trigonal bipyramidal and octahedral are the common geometries for metal carbonyl complexes. Carbon monoxide is a strong ligand and has a tendency to pair up the electrons of the metal atom in the inner orbitals, and thus metal carbonyl complexes are generally inner orbital complexes, and most of them follow 18 electron rule with few exceptions. Techniques used for the determination of structures of metal carbonyl complexes. The structures of homoleptic metal carbonyls such as vanadium hexacarbonyl, chromium hexacarbonyl, iron pentacarbonyl and nickel tetracarbonyl have been established by X-ray diffraction, infrared spectroscopy and electron diffraction studies. The structures of molybdenum hexacarbonyl and tungsten hexacarbonyl have been established by X-ray diffraction studies. The mononuclear metal carbonyls have only one type of linkage, and it is the linear metal to carbonyl bond. The polynuclear metal carbonyls have some other type of linkages also in addition to the linear metal carbonyl bond, such as metal-metal bond and bent or bridging carbonyl bonds. The metal-metal bond has been established by the measurement of magnetic susceptibility and calculation of magnetic moment. The formation of metal-metal bond involves the pairing up of unpaired electrons of metals, leading to the diamagnetism. All the metal carbonyls, whether mononuclear or polynuclear, except vanadium hexacarbonyl, are diamagnetic, that is, they have no unpaired electrons. The presence of bridging carbonyl group in a polynuclear metal carbonyl has been established by infrared spectroscopy. The bridging carbonyl group exhibits infrared absorption in the range of 1700 to 1850 cm inverse due to its stretching modes of vibration. On the other hand, the terminal carbonyl group exhibits absorption peak in the range of 1850 to 2125 cm inverse in the infrared spectrum due to its stretching mode of vibration. Thus, the linear and bridging carbonyl groups of polynuclear metal carbonyls can be distinguished with the help of infrared spectroscopy. Structure of mononuclear metal carbonyls. The mononuclear metal carbonyls have only linear metal to carbonyl linkages, and their structure depends upon the coordination number of the metal, that is, number of carbonyl groups attached to the metal ion and the type of hybridization on the central metal ion. The structure of nickel tetracarbonyl has been established to be tetrahedral from various studies. The nickel atom of this complex is sp3 hybridized. The structure is shown here. The anionic cobalt tetracarbonyl and iron tetracarbonyls are isoelectronic to the neutral nickel tetracarbonyl, and hence they also have tetrahedral structures. The pentacarbonyls such as iron pentacarbonyl, ruthenium pentacarbonyl and osmium pentacarbonyls have trigonal bipyramidal structures arising from dsp3 hybridization on the central metal atom. The anionic manganese pentacarbonyl is isoelectronic to iron pentacarbonyl, and it also has trigonal bipyramidal structure. The hexacarbonyls such as vanadium hexacarbonyl, chromium hexacarbonyl, molybdenum hexacarbonyl and tungsten hexacarbonyl have octahedral structures arising from the D2sp3 hybridization on the central metal atom. Whereas the anionic vanadium hexacarbonyl, niobium hexacarbonyl, tantalum hexacarbonyl and cationic manganese hexacarbonyl also have octahedral structure. Structure of dinuclear metal carbonyl complexes. First, the dimetallic decacarbonyl type of dinuclear metal complexes. The infrared absorption and X-ray diffraction studies on dimanganese decacarbonyl molecule suggest that in this molecule, each manganese atom is directly attached to the other manganese atom by a manganese-manganese sigma bond, which is formed by the linear overlapping of singly occupied D2sp3 hybridized orbitals and 5 terminal carbonyl groups through a linear metal carbonyl coordinate bond. The presence of manganese-manganese single bond in dimanganese decacarbonyl molecule is further supported by its diamagnetic character and short manganese to manganese distances of 2.79 angstrom. Thus, the coordination number of each manganese atom in dimanganese decacarbonyl molecule is 6. This molecule contains a linear linkage which is shown here. At the same time, dimanganese decacarbonyl molecule contains 2 square planar manganese tetracarbonyl moieties in staggered conformation, and hence the point group of dimanganese decacarbonyl molecule is D4D. It is obvious that dimanganese decacarbonyl molecule may be regarded as 2 distorted octahedra sharing one corner. Ditechnetium decacarbonyl and diuranium decacarbonyl also have similar structures to dimanganese decacarbonyl. Dicobalt octacarbonyl structure. The infrared spectroscopy studies made on dicobalt octacarbonyl N-heptane solvent suggest that it occurs in 2 isomeric forms, which are in temperature dependent equilibrium with each other. The 2 forms are shown here as the non-bridge structure and the bridge structure. At room temperature, both bridged and non-bridged structures of dicobalt octacarbonyl are present in almost equal portions. At high temperatures, the non-bridge structure dominates, while at lower temperatures, the bridge structure dominates. The standard enthalpy of conversion of bridge structure into a non-bridge structure is plus 5.5 kilojoule per mole, but it is accompanied by an increase in entropy, so that there is very little difference in Gibbs free energy of the 2 forms of dicobalt octacarbonyl. In the bridge structure of dicobalt octacarbonyl, each cobalt atom is attached to 3 terminal carbonyl groups, 2 bridging carbonyl groups and 1 other cobalt atom. The cobalt-cobalt single bond is formed by the bent or angular overlapping of singly occupied d2sp3 hybrid orbitals of the two cobalt atoms. The cobalt-cobalt distance is 5.25 angstrom and the coordination number of cobalt is 6. In the non-bridge structure of dicobalt octocarbonyl, each cobalt atom is attached to 4 terminal carbonyl groups and one other cobalt atom. The cobalt-cobalt single bond is formed by the linear overlapping of singly occupied dsp3 hybrid orbitals of two cobalt atoms, and its length is slightly greater in the range of 2.7 angstrom due to the absence of bridging carbonyl groups. The coordination number of each cobalt is 5 with trigonal bipyramidal arrangement around it. The X-ray diffraction studies of the crystals of dicobalt octocarbonyl molecule indicates that the molecule has bridge structures. The structure of di-iron nonocarbonyl. The infrared absorption studies and X-ray diffraction studies on the crystals of di-iron nonocarbonyl suggest that in the molecule, each iron atom is attached to 3 terminal carbonyl groups and 3 bridging carbonyl groups and one other iron atom. The iron-iron bond is formed by the lateral overlapping of singly occupied dxy atomic orbitals of 2 iron atoms involving 4 overlap zones, and thus it is a delta bond. The iron-iron distance in this complex is 2.46 angstrom. The coordination number of iron atom in the di-iron nonocarbonyl is 7 rather than 6. Thus, the di-iron nonocarbonyl molecule consists of 2 octahedra sharing a triangular face containing 3 bridging carbonyl groups. Diosmium nonocarbonyl is suggested to have osmium-osmium bond but only one carbonyl group. Structure of trinuclear metal carbonyls. The group 8 metal ions of the periodic table such as iron, ruthenium and osmium form trinuclear metal carbonyls of the type M3 carbon monoxide 12. The X-ray diffraction and infrared absorption spectral studies made on tri-iron dodecacarbonyl suggest that the molecule has following structural features such as 2 iron atoms are linked by a single iron-iron covalent bond. Each of the 2 iron atoms is attached to 3 terminal carbonyl groups. Each of the above 2 iron atoms is attached to 2 bridging carbonyl groups. Each of the iron atoms is attached to a third iron atom by a covalent bond. There are 3 iron-iron bonds of equal length of 2.8 angstrom. The third iron atom is attached to the 4 terminal carbonyl groups and no bridging carbonyl group. The structure is shown here. Tris-ruthenium dodecacarbonyl and tris-osmium dodecacarbonyl have triangular planar arrangement of 3 metal atoms which are held together by 3 metal-metal bonds. Each metal atom is attached to the 4 terminal carbonyl groups and no bridging carbonyl group. The structures of both the complexes are shown here. Structures of tetranuclear metal carbonyls. The group 9 metal ions of the periodic table such as cobalt and iridium form tetranuclear metal carbonyls of the type M4CO12. In the molecule of tetracobalt dodecacarbonyl, cobalt atoms are present at the corners of a tetrahedra. Each of the 3 cobalt atoms present at the corners of a triangular face is attached to 2 terminal carbonyl groups, 2 bridging carbonyl groups and 3 other cobalt atoms. Thus, the coordination number of cobalt atom is 7. The remaining 4th cobalt atom is attached to 3 terminal carbonyl groups and 3 other cobalt atoms and no bridging carbonyl group. Thus, The coordination number of this cobalt is 6. Tetrarhodium dodecacarbonyl has structures similar to that of tetracobalt dodecacarbonyl, but tetrairidium dodecacarbonyl has different structure. 4 iron atoms are present at the corners of a regular tetrahedron, where each iridium atom is attached to 3 terminal carbonyl groups and 3 other iridium atoms, but no bridging carbonyl groups. The structure of the complex is shown here. We can see that the coordination number of each iridium atom in the complex is 6. Electron rule. Sidgwick made an attempt to explain the nature of bonding in transition metal complexes on the basis of electronic concepts. According to him, the ligands act as Lewis base and the metal ions act as Lewis acids. Each ligand usually donates an electron pair to the metal ion during the formation of a complex compound. The complex compounds in which the central metal atom or ion acquires noble gas configuration are stable. On this basis, the effective atomic number rule was proposed, which states as follows: the sum of the electrons on the central metal atom or ion and the electrons donated from the ligands in a complex compound is called the effective atomic number of the metal. And for stable complexes, it is generally equal to the atomic number of next incoming noble gas. We will see lot of examples to establish effective atomic number rule, which is equal to the number of electrons on the central metal atom or ion plus the number of electrons donated by the ligands. For example, the effective atomic number of chromium in chromium hexacarbonyl can be calculated as follows. We know that the number of electrons on the chromium atom is 24 and 6 carbonyls can donate 12 electrons or 6 electron pairs. So, the effective atomic number of chromium in chromium hexacarbonyl will come out to be 12 plus 24, that is 36. Thus, the effective atomic number of chromium in chromium hexacarbonyl is 36, which is the atomic number of next incoming noble gas to chromium, that is krypton. It is obvious that chromium hexacarbonyl obeys effective atomic number rule and hence it is a stable complex. An alternative and more general statement can be given instead of effective atomic number rule as follows. When the central metal ion or atom of a complex compound requires noble gas electronic configuration of n-1 d10 ns2 np6, there will be 18 electrons in the valence orbital or valence shell. Hence, the electronic configuration will be closed and stable. It is known as the 18 electron rule. The complexes obeying the 18 electron rule are quite stable. 18 electron rule applied to the metal carbonyl complexes. The 18 electron rule is very useful in predicting the stabilities and structures of various organometallic compounds. There are two conventions for counting electrons in complexes. First is the neutral atom or covalent method. The second is oxidation state or Ionic model. Both the conventions have almost equal number of supporters and both the methods leads to exactly the same net results. The covalent model is probably more foolproof because it does not require the correct assignment of oxidation states, which is sometimes a difficult job in the case of certain organometallic compounds. Let us illustrate above the two methods by counting electrons in hydrido-cobalt tetracarbonyl complex. According to the covalent model, there is covalent bond between cobalt and hydrogen atoms in the complex, and hydrogen acts as a 1 electron donor ligand. According to this, the number of electron in the valence shell of cobalt in the complex would be 9 electrons from cobalt plus 4 electron pairs from the 4 carbonyl ligands and 1 electron from the hydride ion. Therefore, the sum comes out to be 18. According to the ionic model, there is ionic bond between a cobalt tetracarbonyl cation and hydride ion, and the hydride ion acts as a 2 electron donor. Accordingly, number of electrons in valence shell of cobalt in the complex would be 8 from the cobalt cation, 4 electron pairs from the carbon monoxide and 2 electrons from the hydride anion, within the sum comes out to be 18. The steps that are generally followed for counting the electrons present in the valence shell of central metal in the metal carbonyl complexes are: first, the electrons present in the valence shell of the metal ion, that is n-1d, ns and np orbitals are counted, and then electrons are added to it or subtracted from it depending upon the nature of charge present on the metal carbonyl complex, such as negative or positive. Second, each terminal carbonyl group contributes 2 electrons to the valence shell of the central metal. Third, the bridging carbonyl group M, metal carbonyl M, contributes 1 electron to the valence shell of each metal atom attached to it. Fourth, the metal-metal single bond contributes 1 electron to the valence shell of each metal atom. According to the covalent model of electron count, hydrogen atom, halogen atom and alkyl groups contribute 1 electron each to the valence shell of central metal. The electrons donated by the conventional ligands in the valence shell of central metal are also counted. The electrons counted in the step 1 to 6 are added to find out the total number of electrons in the valence shell of the central metal atom of the metal carbonyl complex. Some examples of electron counting by this method in the metal carbonyl complexes are shown in this table. For example, in the nickel tetracarbonyl, nickel has 10 electrons, whereas 4 carbon monoxide ligands donate 4 electron pairs, giving to a total of 18 electrons on the central metal atom. Likewise, if we take a dinuclear complex such as dimanganese decacarbonyl, each manganese atom has 7 electrons, whereas 5 carbonyl ligands donate 5 electron pairs. 1 electron is contributed by the Mn-Mn single bond. So, the total number of electrons around each metal atom comes out to be 18. Likewise, we can take mixed ligand complexes such as manganese pentacarbonyl methyl, where manganese donates 7 electrons and 5 carbonyl ligands donate 5 pair of electrons. 1 methyl group donate 1 electron. So, the total is 18 electrons on the metal atom. Likewise, in anionic metal carbonyl complexes such as disodium tetracarbonyl ferrate, each iron atom donates 8 electrons plus 4 carbonyl molecules donate 4 pair of electrons and 2 electrons from the 2- oxidation state of the complex. The total comes out to be 18. Hence, the complex is stable. In summary, we can say that the shape of a metal carbonyl complex depends upon the nature of hybridization on the central metal atom. Carbon monoxide is a strong ligand and it can be bonded to the metal atom in 2 different ways, forming metal carbonyl complexes. Carbon monoxide molecule can be coordinated to the metal atom in a linear fashion through a metal carbonyl bond. Such a carbonyl group is called terminal carbonyl group. Carbon monoxide molecule can be coordinated to 2 metal atoms simultaneously, as shown here. Such a carbonyl group is called a bridging carbonyl group. The terminal and bridging carbonyl groups can be distinguished with the help of IR spectroscopy. The terminal carbonyl group exhibits IR absorptions in the region of 1850 to 2125 cm inverse, while the bridging carbonyl group does so in the range of 1700 to 1850 cm inverse. Tetrahedral, trigonal bipyramidal, and octahedral are the most commonly occurred geometries of metal carbonyl complexes. The number of electrons in the central metal of a metal carbonyl complex compound, including those donated by ligands, is called its effective atomic number. The effective atomic number of a central metal in a metal carbonyl complex is invariably equal to the atomic number of its next noble gas. When the central metal ion or atom of a complex compound acquires noble gas configuration of n-1d10, ns2 and np6, there will be 18 electrons in the valence orbital or valence shell, and the electronic configuration will be closed and stable. This is known as 18 electron rule or effective atomic number rule. Most of the metal carbonyls obey 18 electron rule, and hence they are significantly stable. Vanadium hexacarbonyl is the only metal carbonyl which does not obey 18 electron rule and is stable.